Hello everyone, and welcome to this introductory video on wavelet despiking, where I will cover some of the theory and motivations that led to the development of this algorithm. Now, the wavelet despiking algorithm I originally wrote was designed for removing motion artifacts from functional MRI time series. However, as you'll see in later videos, I have now extended this for use with other biological time series. But first, let's take a look at the sources of noise in fMRI data. First, we have scanner noise, which is now relatively simple to account for during time series or data acquisition. Next, you've got noise from cardiac pulsations and respiration. This can be a very significant source of noise, but it can also be effectively modelled and removed from the data. And lastly, we have noise from motion that occurs in the scanner. This can be from movements of the jaw, movements of the eyes, or movement of the head itself. There are 6 non-mutually exclusive planes of movement, 3 translations and 3 rotations, and all of these have theoretically different effects on the time series themselves. Now let's take a look specifically at motion artifacts. I like to subdivide this problem into image processing issues that movement causes and time series denoising issues. So first, to look at the image processing issues. Movement will cause image misalignment and geometric deformation. Now, the latter is particularly significant for large movements, as you can see on the image at the right-hand side of the screen. Because data is acquired in sequential slices of the brain, which takes a given length of time, which is equal to the TR, if a subject moves during this time, the next image, representing the next time point, will be displaced in space. And there are lots of effective rigid body and non-rigid body image realignment algorithms in the literature for realigning these images. So actually this, unless the movement is very large, this is actually a reasonably simple problem to solve. Next, you have the effects on the time series. The first of these is voxel shift intensity changes. And this arises because different parts of the brain have different attenuation or signal strength. So if you translate the brain, or move the brain, from one given point in space to another, you can end up collecting information from different voxels, which all have different baseline signal intensities. And this shows up in the time series as stepwise changes. Next, the actual signal itself in fMRI time series comes from alignment of spins. So if you move and the spins dephase or are now not in alignment with each other, you lose signal. And this causes a downward deflecting spike, or a negative spike, as I call it. And related to this, you get spin history effects, which are related to the time taken for spin rephasing after dephasing. And it's seen in the time series as a spike and drift back to baseline. So here I show you the 3 types of artifacts in the time series: the voxel shift intensity change, which causes stepwise changes in the signal intensity change, which causes negative spikes, and the spin history effect, which causes a spike and a slow drift back to baseline. To make things even more complicated, the time series themselves are non-linearly related to physical movement. So for example, for a given movement, you might observe a small spike at the front of the brain, but a large spike at the back of the brain. And as I've just described, the artifacts are spatially inhomogeneous. And in addition, they are present variably in different frequencies. And that's particularly true of spin history artifacts, which, as I described earlier, are seen as spike and drift type artifacts. And you'd expect those to be seen in high and low frequencies. So modelling these artifacts is near impossible. But the one thing they do have in common is that they are non-stationary. And the non-stationarities caused by motion artifacts are larger than the endogenous non-stationary fluctuations. And this is actually the fundamental assumption behind wavelet despiking. The field has known about the problem of head movement since the 1990s, and a significant amount of work was done on this at the time. And the solutions that were created, which tended to revolve around linear regression of physical movement time courses from the fMRI time series themselves, were thought to be largely adequate to mitigate the effects of movement. However, as some of you may be familiar, in 2012 the head movement problem resurfaced in a significant way when 3 high-profile papers demonstrated that the methods that had been used in the field for the prior 2 decades were probably inadequate, And in high motion datasets, they resulted in a bias of functional connectivity, whereby nearby regions of the brain had artificially enhanced connectivity, but distant brain regions had artificially reduced connectivity. And in this case, connectivity refers to any measure of association between the time series, such as the Pearson correlation. Now, it's fairly easy to see how such a bias might arise. If we consider a simple example whereby a subject has performed a pitch movement in the scanner, the front of the brain would move more than the pivot point. This means that movement artifacts are likely to be more similar in neighbouring voxels at the front of the brain. In this example, you can see that these spikes in voxels at the front of the brain, which are caused by movement, are then causing an artificially enhanced correlation between the time series from the green and orange voxels. Now, if you applied linear regression to these time series, or regression of the movement time courses to these functional time series, you could see how it would be potentially easy to overfit the time series from the white voxel, but potentially underfit the time series from the green and orange voxels. This relates back to the point I made earlier about nonlinearity. The bottom line is that if you don't adequately remove the artifacts, you will end up with a bias. And this leads me on to wavelets. So why are wavelets particularly good for solving this type of problem? Well, wavelets are useful for fractal and 1/f or long memory processes, both of which apply to functional MRI. They provide multi-resolution decomposition of signals and are good at detecting transient non-stationarities. If one were to use a Fourier transform on a spike, you'd end up aliasing the spike into other frequencies, because the Fourier transform fits a set of sinusoidal bases to the spike, which of course doesn't fit the profile of the spike at all. So the Fourier transform of a spike is white. And the last property of wavelets that's particularly useful is the decorrelating or whitening properties. Functional MRI time series are autocorrelated, heavily autocorrelated, so estimating degrees of freedom requires whitening. But I'll come on to this in the next tutorial. The wavelet despiking algorithm is actually based on a very well-known method called the wavelet transform modulus maxima method. It was originally developed by Mala and Huang in 1992 for image processing, but has since been used extensively by astrophysicists and oceanographers for detection of rare events, which of course are seen in the time series as non-stationarities. So how does it work? Well, first, the time series is decomposed into a set of wavelet coefficients. The y-axis in this image represents scale or frequency band, and the x-axis is time. Then a chain search algorithm looks for modulus maxima and also minima across the wavelet scales, and looks particularly for chains of these coefficients. It then splits this set into two additive sets, one representing the noise coefficients and one representing the signal coefficient. These masks are then used to perform something called hard thresholding, where coefficients that are not needed are set to 0 before recomposing to form the original time series. So now the time series can be reconstructed from the wavelet space to produce noise signal, which is seen on the left, and the denoised signal on the right. So how effective is it? Well, this figure is taken from the 2014 paper in which this method was originally published. The 3 columns represent data from different patients, and the middle row takes a single voxel-wise time series from the prefrontal lobe of the brain in each of these patients. Now, when you compare the time series to the time course of physical movement, which you can see in the top row, you can see that areas of the time series where large non-stationary events are present correspond to points in time where the subject has moved. In this figure, I compare the output of wavelet despiking, which is seen at the bottom, with output of a temporal despiking algorithm, which is shown in blue, and has been published and used for removing motion artifacts in the past as part of the AFNI software. Now, this is by no means the only algorithm for despiking time series in the literature, but it provides a useful comparator here to wavelet despiking because it attempts to achieve the same goal. Now, the problem with the time despike algorithm is that it looks for specific spike patterns, and as I mentioned earlier, we know that motion artifacts are very inhomogeneous, which can take on a number of different and unpredictable forms. What is nice is the remarkable efficiency with which wavelet despiking handles a range of different non-stationary motion artifacts. So, to summarise, the algorithm is spatially adaptive, i.e. only despikes artifacts in part of the brain where they occur, and thus avoids the overfitting problem. It's data-driven and model-free, which is a good thing, because as I described earlier, it is very difficult to model motion artifacts, and it performs excellently when left unsupervised. So now if we go back to our original example containing locally similar motion artifacts, and we successfully denoise the artifacts, we can get rid of the connectivity bias. Now just to end, I'll show you one of my favourite summary figures. And here what I've done is plotted the standard deviation of each time series on a cortical surface map. And you can see very quickly which areas are affected most by motion. In this case, it's the posterior part of the brain that's particularly affected, as you can see from the smaller brain at the top right of the screen. And after applying a voxel-wise wavelet despike, you can see how effectively the areas of increased variance caused by motion are reduced. And importantly, the despiking algorithm only reduces the variance in regions where the artifacts actually occur. So if you want to give the algorithm a try, it's free to download as part of the Brain Wavelet Toolbox at www.brainwavelet.org. And in the next tutorial, I will cover probabilistic analysis using wavelet despiking.